So in this video we will see how to calculate the flux density along the axis of solenoid carrying current. So first of all we'll know what is a solenoid. Okay, you see, actually the solenoid is a type of circular coil in which it has n number of turns. This structure is called a solenoid. This is the axis and this is a solenoid. Usually solenoid is used around the nails, like this. It is used around the nails for wrapping it and then producing the electric current, usually to produce the electromagnetism in the nail. But here we'll calculate the flux density through this solenoid. So see, solenoid is something like this. Now if we assume it in a diagrammatic form, then we'll see this is the axis of solenoid, and now we'll put here dots, okay, on the either side. These dots are representing this solenoid's turns. Like this, if we connect, it will form something like this. Okay, so for diagrammatic form we are representing it in this way. The dots are there. Okay, so this will be uv. You can assume it anything. Uv, this is mn, you can assume it anything. Now see, we need to calculate the flux density along this axis. So first of all, let's consider this infinitely long solenoid, uniform solenoid. Not infinitely long now, just assume it as a solenoid having uniform number of turns. Now see, the number of turns here, so the number of turns here will be n. As I said in the very first video, that n is for number of turns and capital N is for number of coils. So here it is a turn, so we'll assume that this solenoid has n number of turns, each of radius a. Okay, this radius is a, this radius is a. Okay, this radius is a. For turns and circular coils we are using the radius a. In the very first video, in the first two applications, we saw that when we were calculating the flux density along the center of the circular coil and along the axis of the circular coil, then we were using the radius a. You can see we were using the radius a. Okay, so here also we are using the radius a for circular coil and turns. So see, here it comes for the turns, so we are using the radius a. And then now we'll assume that I current is flowing through them. So we need to calculate the flux density along the axis at any specified point. So let us consider a specified point P. Okay, and as I said, after considering the specified point, we always have to mention about the elemental length. So see, this is P, and now we'll say about the elemental length. Let us assume the elemental length to be here AB, and the midpoint of the elemental length and the specified point are always joined. So these two are joined such that this angle is alpha. Okay, such that this angle is alpha. Very clear till now. Specified point, elemental length, and they are joined such that this angle is alpha. Now as we did in the solenoid, as we did in the straight conductor carrying current, we did that. See, the specified point and the ends are joined. Similarly, we'll also join the ends out here. Now the ends will be joined. Okay, ends are joined in such a way that this angle is alpha 1 and this angle is alpha 2. Okay, as we can see in the figure, now see, this angle is alpha 1. Okay, this angle is alpha 1, which is connected to the end M, and this alpha 2 is the angle which is connected the specified point and the end N. It is alpha 1, and from here only it is alpha 2, and this angle is alpha, as we said. Now see, now the another assumption comes here. Now the last assumption for this figure. So see, this is the point O. Okay, now point O. Now this U to O is X and U to P is X dash. This is the last assumption. So this point U, and starting of the conductor, I mean solenoid, to this point O, it is X, and U to P is X dash. You can see in the figure as well, it is U to O is X and U to P is X dash. Now we'll go for the description. As we can see, the description is very simple. So let us consider a uniform solenoid having n number of turns per unit length, in which each coil has radius A and current I. As I said, each coil has radius A and current I is flowing through them. Okay, and then we can see that the specified point is taken. Let P is the point along the axis of solenoid where the flux density is to be obtained. Then immediately after saying about the specified point, we need to say about the elemental length. So let A be equal to dx is the elemental length. Now see, here comes the exception. In all the previous applications we were taking the elemental length to be AB equal to dl. Here we are taking AB equal to dx. No worries, we can take dl as well. No any change will come in the formula. The formula will still remain the same. We can take dl, but universally they are taking dx, so we'll also take dx. But if you get confused, you can take dl as well. Okay, so now see, elemental length is dx. So let AB equal to dx is the small elemental length of the solenoid, which has n dx number of circular coils within it. Now see, what is the logic behind n dx number of circular coils? Now see, we are saying that this turn is per unit length. Now that means that in unit length, in 1 cm or 1 meter, anything in 1 unit, there is one turn. Okay, so see, in this much total we have n turns. Okay, and this distance is dx, so total turns in this AB will be n into dx, n dx. Now I'll repeat this again. See, we are saying that this circular coil, this solenoid, has turns in per unit length. It means that if this is 1 cm or 1 meter, anything, it has one turn in it. Now when we are mentioning about the elemental length, then elemental length is dx. Okay, dx, this much is dx, and total number of turns is n. So in this much area, how many turns are there? So for that we will multiply n into dx, n dx. So in this AB we have n dx number of turns. Let's go further. So see, let C is the midpoint of AB, and C and P are joined such that in this angle CPO equal to alpha. So angle CPO equal to alpha. As I said, this angle should be alpha. Okay, alpha. And then the ends P and M and P and N are joined such a way that angle UPM is alpha 1 and angle UPN is alpha 2. Okay, so now we have done all the figure description. Now we'll go for the calculation. Now here comes the biggest exception in all the applications. In all the applications we were directly using the Biot-Savart's law. It was dB equal to mu naught by 4 pi IDL sine theta by r square. Okay, we were doing this, and then we were calculating the values of dl, sine theta and r. We were putting the values there. Okay, but here we'll not do that. Here we'll directly write the flux density along the axis of circular coil. Now what I mean from that is that, see, we'll directly write according to Biot-Savart's law, dB equal to mu naught Ia by 2 r square sine alpha into n dx. Now why I have written this here in the very first step, why I did this here, because now see, this is a type of circular coil. I said in the very beginning that it is a type of circular coil. It has many turns. Okay, now see, for the flux density along the axis of circular coil, we had calculated the formula to be this: B equal to mu naught Ia square by 2 a square plus x square to the power 3 by 2. This was the formula for flux density along the axis of circular coil carrying current, isn't it? Now see, here it is a type of circular coil. We are calculating along the axis, so we will use this formula. But see, the formula is slightly different. Here it is mu naught Ia by 2 r square sine alpha. Here it is something else. Now if you turn a page behind, now you can see that in this equation 2, what we did in a circular coil, this is the same equation we are using here. Now see, I'll say what we have done here. In circular coil carrying current, if you remember, we first wrote about the Biot-Savart's law, and then we put the values there. See, we had done the dB sine alpha. We need to integrate dB sine alpha because it is the only effective thing there. So we'll integrate dB sine alpha to get the total value of flux density. We integrated dB sine alpha. We put the value of dB there. This dB was put there. and then we integrated and it came this way. Okay, and after that we calculated the value of sine alpha and r, and then we put the value, and the final expression was this. But initially the expression was this: b equal to mu naught ia by 2 r square sine alpha. Now this formula we are using here. Okay, this formula we'll use here because this both are the same thing, axis of circular coil, axis of circular coil. It is just that it is formed in the form of solenoid, it is just a circular coil, so we'll use this formula here. Okay, and see what is the logic behind multiplying n dx, because this is the flux density. Now the flux density should be multiplied by this elemental length. Okay, so see, this is the flux density along the axis of circular coil for one circular coil, isn't it? Now see, within this elemental length we calculated there are n dx number of circular coil, so we'll obviously multiply by n dx. Now again I'll repeat what we have done, just the figure AB. Now see, AB has n dx number of circular coils. Okay, now the flux density along the axis of circular coil is mu naught ia by 2 r square sin alpha multiplied by n dx, because we are calculating the flux density at P due to this elemental length. Okay, so now this is our formula. Now we just need to put the values of some terms as we were doing earlier. Now see, here comes a trick to remember. I'll show you the trick. So see, at the center of the circular coil we put the value of nothing. It was just dB equal to mu naught by 4 pi ideal sin theta by r square. We integrated it within the respective limits. We calculated the final value. Along the axis of circular coil, after getting the value of dB equal to mu naught ia by sin alpha 2 r square, we put the value of r and sin alpha. In straight conductor, after getting the value of dB, which was something like this, we got the value of dB to be mu naught by 4 pi ideal sin theta by r square. Then we put the value of sin theta, and then we put the value of r, and then we put the value of dl. So see, we put the value of sin theta, we put the value of r, we put the value of dl, and in this one we need to put the value of r, and we need to put the value of dx. Now see, again, in center of circular coil nothing, in axis of circular coil sin alpha and r, in straight conductor sin theta, r and dl, in this r and dx. Okay, now with this one there is no other way. We need to remember this, in which application we need to put the value of what we need to remember, and it will come from practice, only practice. So see, nothing, in axis of circular coil sin alpha and r, straight conductor sin theta, r and dl, and solenoid r and dx. So see, this is our expression. Okay, now we'll put the value of r and dx, only these two. Okay, now see, first we need to calculate these two values. Again we'll go in the triangle. Now let me make the figure again, just to be clear. Now see, here is the figure again. So again the figure was just simple: PAB joined CP, so that CP equal to r. This is radius A, alpha 1, alpha 2, this is x, and this is x dash. Now see, we need to calculate the value of r and dx. So see, for r we'll see the triangle again. Okay, very simple, we'll see the triangle. Now see, we need to put the value of r. So in what relation r will come? We can use sin alpha equal to a by r. Okay, because sin alpha equal to p by h, so sin alpha will be equal to p by h, a by r. So sin alpha will be equal to a by r. Just not to get confused, I'll show you in earlier what we did. For calculating the value of r, in the very first one, in the axis of circular coil carrying current, for r we did r equal to a square plus x square, Pythagoras theorem. In the flux density due to straight conductor carrying current, for in this one we did, for r is cos alpha, we used cos alpha equal to a by r. This figure we used cos alpha equal to, in this figure we used cos alpha equal to a by r. Okay, so in this we used cos alpha. In this one figure we'll use sin alpha equal to a by r. Simply we need to calculate the value we need to calculate the relation in which a and r both are coming. So see, in this figure a and r both are coming in the relation sin alpha, so sin alpha will be a by r, so r will be a by sine alpha. So we got the value of r. Okay, now the remaining is value of dx. So for value of dx, see what is dx. Dx is actually this length, elemental length. For that, what we can do is we can calculate the value of x, then differentiate it to get value of dx, as we did in the straight conductor carrying current. See, in straight conductor carrying current, we needed the value of dl. Okay, we needed the value of dl. For that, what we did, we calculated the value of r and then differentiated it with respect to alpha, then we got dl. If you are still confused, see my last video. In that I have shown how to calculate the flux density due to straight conductor carrying current. Okay, so see further, what we had done. um, yeah, as I said that. So similarly, we'll calculate x here and then differentiate it to get the value of dx. So see, x so x, we need a relation in which x will come now. So for x, what we can do is, so this is, if this is x and this is x dash, this can be x dash minus x, obviously, and we can use, this is b and this is p, perpendicular and base. So we can use tan alpha equal to p by b. Okay, so we can use tan alpha equal to a by x dash minus x. So now see, there is a trick here. For always calculating this elemental length, one thing, dl dx, will always use tan. Okay, only in two applications we need to calculate this, so it is very easy to remember. In straight conductor carrying current, we needed to calculate, so we used tan alpha equal to a by l by a. Here also we will use tan alpha. It's very simple. Whenever we are calculating these values r and l and dl, we need a relation in which a is also there. So see, in this straight conductor, the relation in which a and r was there, it was cos alpha. Similarly, a and l was there, it was tan alpha. In this figure, the relation in which a and r was there, it was sin alpha, and the relation in which a and x will come, it is tan alpha. Simple. So tan alpha equal to x by x dash minus x. Now let's do from a fresh page. You see, so we got the values of tan alpha. We got the value of tan alpha. Okay, so it was tan alpha equal to a by x dash minus x. We need the value of x, remember. So x dash minus x equal to a by tan alpha. We need the value of so 1 by tan alpha is cot alpha. A cot alpha. Yeah, isn't it? Now see, we need the value of x. We said that we can differentiate it to get the value of x. So now differentiating this with respect to alpha, as we did in the previous one. So this will be d x dash minus x. Now see, one thing, x dash is here constant. Okay, now see, x dash is constant in this figure. X dash is constant. The value of this, I mean the specified point and the starting of the solenoid, it will always remain constant, because we are taking one specified point. Okay, so this value will always remain constant, x dash. Obviously specified point is not gonna change anyhow. Yeah, x can change, because we can take elemental length anywhere. We can take elemental length here, we can take elemental length here. So see, this x dash is constant, but x is not constant. Okay, x is never constant. So now see, on differentiating this, we'll get dx dash by d alpha minus dx by d alpha will be equal to, now see, a will come outside. A is also constant, it is a radius. So it will, now see, this is constant, it will become 0. So it will be minus dx by d alpha will be equal to, now see, it is a, and differentiation of cot alpha is cosec square alpha minus cosec square alpha. So it will be minus cosec square alpha. We need to remember the differentiation calculus and mathematics for this. So minus dx by d alpha will be minus a cosec square alpha. Okay, now see, minus minus cancel, and dx will get the value of dx to be a cosec square alpha into d alpha. This is the value of dx. Now we got the value of r, we got the value of dx, and as I said, in this solenoid we only need these two values, so we'll keep these two values there. So our expression was, once again I'll revise why that expression came. So see, it is a type of circular coil, so we use the expression of circular coil, mu naught ia by 2r square sine alpha, and see in the elemental length there are n dx number of turns, so we are using n dx. Okay, now we need to put the value of r and dx. The value of r, once again we got the value of r to be a by sine alpha, if you remember, and the value of x dx was found to be a cosec square alpha d alpha. Now we'll put the values there. Okay, so it will become mu naught I a by 2 into, it will be a by sine alpha whole square. So sine alpha will remain as it is, and then n will also remain as it is. Dx, the value of dx is a cosec square alpha d alpha. So now see, now just the calculation is left. Now see, we are just doing the calculation. So it will be mu naught ia by 2a square sine square alpha sine alpha dot n dot a cosec square alpha d alpha as it is. Now see, the calculation will be somehow like this. N a square, a cancel, a and a cancel. Okay, so mu naught ni by 2 will remain. Now see, sine alpha and this cancel. No, it will not get cancelled, sorry. So it will go up and multiply, so it will become sine cube alpha cosec square alpha and d alpha, isn't it? Now see, as we know that cosec square alpha is 1 by sine alpha, isn't it? Cosec alpha is 1 by sine alpha, so cosec square alpha is 1 by sine square alpha, so it will be 1 by sine square alpha. Then it will get cancelled, so remaining will be sine alpha d alpha. So this will be remaining. Okay, this is our expression for dB, what we'll get. And now, as we know, it is very simple. When we get dB, then we'll just integrate it within the respective limits to get the value of total flux density. So now we have the value of dB, which is mu naught ni by 2 sine alpha d alpha. Okay, now we'll just integrate it within the respective limits. Now, as I said, respective limits is a matter of concern, so in the, we can see behind, we need to compare and study, so that we do not get confused. So see, in the first it was 0 to 2 pi a, very simple. As I said, perimeter should be taken 0 to 2 pi a, because we are calculating the flux density to the entire length of the conductor. In the second one also it was 0 to 2 pi a. In this it was minus alpha 1 to alpha 2, because see, the angle's direction, the current is going this way. Okay, if the current is going this way, then one angle is going this way and one angle is going this way, so one needs to be taken in negative. So see, this will be minus alpha 1 to alpha 2, minus alpha 1 to alpha 2, because the current is in one direction and the angle is in opposite direction. So see, alpha minus alpha 1 to alpha 2. Now in this one we can see it will still remain the same, alpha 1 to alpha 2, but here minus will not come. Also why? So see here, as I said, the entire length should be taken. So for entire length, obviously this whole is the entire length, so alpha 1 plus alpha 2 needs to be taken, yeah, because the entire length is taken. So alpha 1 plus alpha 2, but see here the angles are in the same direction, alpha 1, and from here it is taken alpha 2, so the angles are in same direction, alpha 1 alpha 2, so it will be alpha 1 to alpha 2, no minus, alpha 1 to alpha 2. As I said, these two, the last two applications are same, the first two applications are similar, not same, similar. But now we'll see, the limits will be alpha 1 to alpha 2, no minus, as I said, alpha 1 to alpha 2, no, alpha 1 to alpha 2 dB, and then we'll put the value of dB here. Now see, the constant term will come outside, the constant term came outside, alpha 1, alpha 2, sine alpha, d alpha, as I said. Okay, and now only the calculation, sine alpha का integration क्या होता है, minus cos alpha, so it will be mu naught ni by 2 minus cos alpha, and then alpha 1 to alpha 2, so upper value minus lower value, mu naught ni by 2, so upper value is minus cos alpha 2 minus cos alpha 1. Okay, so see, sorry, minus one more bracket. So see, minus cos alpha 1 minus, so minus cos alpha 2 minus cos alpha 1 minus cos alpha 2 minus cos alpha 1. So see, minus minus plus, it will be mu naught ni by 2. So minus minus plus, it will be cos alpha 1 plus cos alpha 1 and minus cos alpha 2. Okay, so this is our final expression. So b equal to this is our final expression. So see, this is our final expression, as I said. Now remaining is the special case. The special case is same as that of the straight conductor carrying current if the solenoid is infinitely long and if the specified point lies at any one end of this solenoid carrying current, infinitely long solenoid carrying current. So see, if the solenoid is infinitely long, if the solenoid is infinitely long, then obviously if, one angle will be 0 degree. How say alpha 1 will be 0 degree, obviously, because if it is infinitely long, then one angle will be 0 degree, there will be no other angle. So see, if it is infinitely long, then this angle will be 0. How? I'll show you. See, if it is infinitely long, it is going in, then obviously the specified point P, and this is the angle, isn't it? So this is the angle, but if it, sorry, this end is the angle, okay, alpha 1. But if it is infinitely long, then obviously this angle will go this like this. ये इधर चलते रहेगा एंगल. अगर ये infinitely long है, अगर infinitely long है तो पॉइंट P आई है, अगर ये infinitely long है, अगर ये उधर जाते रहे तो ये कनेक्ट कब करेगा? कनेक्ट कर ही नहीं पाएगा. ये कनेक्ट लगभग नहीं ही करेगा. ये इधर जा रहा है इन्फाइनेटली लॉन्ग, तो ये पॉइंट पे एंड में कनेक्ट करने की कोशिश कर ही नहीं पाएगा, लगभग ऐसे रहेगा. सो दिस अल्फा 1 विल बी 0 डिग्री. नाउ सी, इस तरफ भी इन्फाइनेटली लॉन्ग. सो अब ये जो एंगल है, ये इधर कनेक्ट करने जाएगा, करते कहाँ पे कनेक्ट करेगा? ये तो इन्फाइनेटली लॉन्ग है, कनेक्ट कहाँ पे करेगा? पता नहीं कहाँ पे करेगा. सो दिस विल ऑल्सो बी स्ट्रेट. वी आर मेजरिंग फ्रॉम दिस साइड, इजंट इट? सेम एंगल. और इसी वजह से वहाँ पे माइनस नहीं है लिमिट्स में, अल्फा 1 टू अल्फा 2 में. इसी वजह से यहाँ पे प्लस, बिकॉज वी आर मेजरिंग फ्रॉम द सेम डायरेक्शन. So see, same direction, it will go this side. Where it will go, we don't know. So it will be 180 degree, isn't it? Alpha 2 will be 180 degree. So if it is infinitely long, alpha 1 is 0 degree and alpha 2 is 180 degree. Just put the values there. Alpha 1 0 degree, alpha 2 180 degree. So obviously we'll get the value of this. Now if the specified point lies in front of any one end of the solenoid, then we can see that if it is lying at any one end, see, this is the specified point. If it is lying at any one end, this is one end. So see, this angle will be, we are connecting both the ends, isn't it? So alpha 1 will be obviously 90 degree. Alpha 1 is 90 degree. And see, we are dealing about the infinitely long solenoid. So it is again going this side. Abhi kahan pe meet hoga pata nahi. So it will go like this. So alpha 2 will be 180 degree. So obviously one angle will be pi by 2, one angle will be pi. So then if we calculate, if we calculate, our final value will come this. So this is all about the applications. And the toroid carrying current, we do not need to study about toroid carrying current. It is never going to ask in examination. So finally we concluded about our applications of Biot-Savart's law. The only thing we need to remember in all these are, for summation, I am saying that all these are just Biot-Savart's law, and then put the values. In center of circular coil, nothing. In axis of circular coil, put the value of sine alpha and r. Okay, sine alpha and r. In straight conductor, sine theta r and dl. In solenoid, r and dx. So I am seeing one trick here. अभी बना रहे एक trick से देखो, sine alpha and r का डाले हैं, साइन थीटा आर एंड डी एल का डाले है, आर एंड डी एक्स का डाले. सो ऐसा करते हैं, इसको हम लोग रेफरेंस लेते हैं. साइन थीटा हम लोग इसको रेफरेंस लेंगे, साइन थीटा आर एंड डी एल को, तो पीछे एक होगा, आगे एक होगा, है ना. सो साइन थीटा आर एंड डी एक्स, दिस इज स्ट्रेट कंडक्टर इज रेफरेंस. स्ट्रेट कंडक्टर के पहले क्या होते थे? एक्सिस ऑफ सर्कुलर कॉइल. सो पहला दो साइन एंड आर, वी आर कैलकुलेटिंग अबाउट साइन एंड आर. ओके, वी आर कैलकुलेटिंग द वैल्यूज ऑफ साइन एंड आर. वैसे स्ट्रेट कंडक्टर के बाद क्या आता है? सोलोनॉइड, यानी कि लास्ट का दो, आर एंड डी एक्स. नाइस ट्रिक, आई थिंक मेरे हिसाब से तो अच्छा ही ट्रिक है. साइन थीटा आर एंड डी एल, दिस इज आर रेफरेंस साइन थीटा आर एंड डी एल। सो पीछे क्या आता है इसका एक्सिस ऑफ सर्कुलर कॉइल। सो पहला दो साइन थीटा एंड आर, साइन थीटा एंड आर। ऑब्वियसली यहाँ पे थीटा यहाँ पे अल्फा, वो तो अब फिगर बनेंगे तभी पता चल जाएगा। सिंपल साइन थीटा एंड आर, और पीछे वाले में इट इज़ ऑब्वियसली आर एन डी एक्स। वो फिगर बनेंगे तो डी एल कहाँ पे है, डी एक्स कहाँ पे साइन थीटा है, कहाँ पे साइन अल्फा है, वो सब पता चल जाएगा। अगर नहीं समझे अभी फिर भी कन्फ्यूज हो, पिछला वीडियोस देखिए। एंड प्लीज़ अगर कोई कन्फ्यूजन और क्वेरी हो तो प्लीज़ इन्फॉर्म मी कमेंट सेक्शन और पर्सनली इन मैसेज। थैंक यू।